Okay, so today we've got to go through chapter 5. Um, the first test has been graded. Please look over your submission. You can check the feedback that I left for you. Any questions you have on it, definitely reach out. I've got 3 Zoom sessions lined up this afternoon with students that want to go over their tests. So just know that I'm very happy to do that if you want to do that sometime. Um, but we're back to kind of our normal schedule. And what I mean by that is we're going to do chapter 5 today, which means the chapter 5 quiz, which is technically quiz 4, because remember, we didn't have a quiz for chapter 4. So anyway, the chapter 5 credit quiz in the chapter 5 folder. That'll be due Monday at midnight. So just we're kind of getting back to that normal schedule of we go through a chapter, the credit quiz is due within a week. There's a lot to cover in this chapter. We've got to go through double displacement reactions, some redox, molarity as a conversion factor. So I'm going to go ahead and get started. The chat box is open if you have any questions, but solution concentration. So what we've learned so far when it comes to stoichiometry, we saw quite a bit of this on the first test, is that if we're going to relate the mass of a substance to the moles of the substance, right, we use the molar mass from the periodic table. And that conversion typically works really well for most students. It becomes very familiar. But now what we have is instead of a solid, we're going to be dealing with solutions. And solutions are marked AQ, right? It's something aqueous dissolved in aqua. It's in water. So we need to have some kind of conversion factor that tells us, okay, if I use this volume of this solution, how many moles of what's called the solute, the important stuff, right? The thing that's actually doing the reaction, not the water, but the solute, how many moles of solute would be in that volume that I've used. So if we're going to relate the volume of solution that we've used in the reaction to the number of moles of technically what's called the solute, the moles of the solute present, now we have to use a conversion factor called molarity. And, for those of you in my face-to-face lab, you've been seeing this for the past 2 labs. We've been looking at solution concentration. So just some terminology here. So a solution is made up of 2 or more components, but at least 2. The solvent is whatever's present in the majority. So when you get into Chem 2, you'll start looking at solutions where water is not always the solvent, because it doesn't have to be. In that case, it's just whatever is present in the greater quantity, that is the solvent. For us, however, because we're dealing with aqueous solutions, the solvent for us is always going to be water. So we're not going to have to worry about situations where it's not water until Chem 2. The solute is just whatever is dissolved in the water. And technically, there can be more than one solute, right? But for the solutions that we're going to be looking at, for the reactions we're going to be looking at, it'll just be one solute. So we started to see this in equations, right? Something that's marked AQ. If it's marked AQ, something like, NaCl and then AQ, that just means that the sodium chloride is dissolved in water. So that makes it a mixture, right? A solution. Homogeneous mixture is often called a solution. And in that solution, the water is the solvent, the sodium chloride is the solute, and molarity, our new conversion factor, would tell us the moles of sodium chloride present in the liter of solution. So for every liter I use, I would know how many moles of sodium chloride I have. Now, dilute and concentrated, these are just relative terms, right? Dilute, you probably are familiar with this. It's not very concentrated, which means molarity is going to be very low. There's not a lot of solute present for a certain volume of solution. If it's concentrated, it's the opposite. Your molarity is going to be really high, and it means there's a lot of solute dissolved per liter of solution, or however much volume you're looking at. But those are just relative terms. It's not like I could say, hey, if the molarity is 0.5, then it classifies as dilute. It really depends on how well the solute dissolves. And so we don't worry about that. They're just relative terms. So molarity is defined as the moles of the solute per liter of solution. And so just knowing here, the solution is both components mixed together, like it would be the salt and the water all combined. That's the solution. So the solution, just for definition's sake, is equal to the solute added to the solvent. It's both parts, right? It's everything. So first thing we're going to look at here is just understanding how to calculate molarity. All right, I'm going to highlight this formula because this is definitely something, again, you've seen it before, but we're definitely going to be using it a lot in this chapter. So question here says, let's find the molarity of a solution that has 3.00 moles of potassium iodide in 2.39 liters of solution. So what I want to just point out is when you're asked to solve for molarity, you want to use the formula. So because we want to know what the molarity is, we're going to use molarity equals moles per liter or volume, right? But we definitely have to have it in liters in the denominator. So this one's really easy. We got 3.00 moles of the potassium iodide in 2.39 liters of the solution. So all we're doing here is basically plugging and then trying to figure out sig figs, which 3 for both. So there's not really much to think about here. So we got 1.26. Now the units here, you can abbreviate with a capital M, that is molarity, and then the solute Ki, or you can label it as 1.26 moles per liter Ki. So just know that capital M is the abbreviation for moles per liter. All right, so you're going to see this on the quiz, the credit quiz and such, when you have to type in your work. If you give me capital M, good. And if you give me mole per liter, good. But you know how the system's only looking for one of those two. So if it marks you wrong, just know I'm gonna go back and fix it. But these are interchangeable, capital M or mole per liter, both the same thing. So this is probably not a calculation we're going to do very often, because when we go into lab and we've got a solid solute like potassium iodide, we're going to put it on the scale and we're going to figure out how many grams we have, right? Not how many moles we have, but we'll measure how many grams. So that's this question here. Let's find the molarity if we use 0.522 grams of HCl dissolved into 0.592 liters of solution. So again, if we're finding molarity, you want to use the formula. Molarity is moles per liter. So we've got the liter part here that's going to go, oh, okay, yes. So some things coming up in the chat that the weather's looking pretty bad. I'm up north in Carrollwood in Tampa, so it's not here yet. But yeah, I have heard it's going to be a stormy day. Okay, so we've got the volume of solution in liters. That's straightforward. We're just going to plug that into the denominator. The only thing we're going to have to do up front here is because we've got grams of HCl, we're going to have to change it to moles. And that's a simple conversion. We're used to it. We just use the molar mass from the periodic table. So you can do this piece by piece, right? You could convert the 0.522 grams of HCl to moles, and then use that answer to go into the numerator, and then the 0.592 into the denominator. Instead of doing it part, one part at a time, what I like to do is whatever quantity of solute I'm given, I just put it in the numerator. Whatever quantity of the solution I'm given, I put that into the denominator. So I've got the solute on top, and then I've got the solution on the bottom. And then I check my units. And it's like, okay, well, liters is good. That's what I need. But grams, I've got to change to moles. So I know that I'm going to set up a conversion step here to get rid of grams and go to moles. And that should look familiar. It's molar mass from the periodic table. So if I go and add 35.45 for chlorine and 1.01 for hydrogen, I get 36.46 for the molar mass. All right. And again, just coming right from the periodic table. All right, so I'm going to take 0.522 divided by 0.592, and then also divided that by 36.46, and I get to 3 sig figs, 0.0242. And again, feel free to abbreviate capital M or 0.0242 mole per liter, and then the HCl as the solute. All right, so just make sure that if you're solving for molarity, that you want to use the formula, and you want to make sure you've got the moles of the solute over liters of solution. Now, what happens in the next example is the molarity is actually going to be given. And it says instead, how many grams of KOH, potassium hydroxide, are required to make 2 liters of a 6.00 molar or molarity KOH solution. So this one's a little bit different. So what I want to say because this always helped me kind of keep it together, is that molarity to me reminds me of density, where if I'm asked to find the density, I would take mass divided by volume and I would get the density. But if density is given to me in the problem, then we saw how it worked as a conversion factor, and it could help us with mass to volume conversions. So molarity is the same way. If I want to find the molarity, I'm going to take moles divided by liters. But if molarity is given to you, then it's going to work as a conversion factor. And remember that the 6.00 capital M really stands for the moles of the solute per liter of solution. And remember that per is an equivalence line, so it equals. So what I understand about this 6 molar concentration is that if I used 1 liter of the solution, which I always abbreviate as SOLN, if I use an entire liter of the solution, in that liter there were 6 moles of KOH. And that means if I only used half a liter, I would only have 3 moles of KOH. But this allows me to understand in the volume of solution that I use how many moles are actually present. So what we're doing here is the calculation I used to do all the time when I would prep all the solutions for lab. Now we have people that help us do that, which is nice. Okay, I have a target molarity that I need for my lab setup. I need about this much volume for all my labs, but KOH comes as a solid. So how many grams of KOH will I need to put into 2 liters of solution, right? Or, just water to get the concentration to 6 molar. So how do we solve this? What I always suggest is you never start dimensional analysis with a conversion factor, right? We always start with the measurement. For a chemist, that's typically going to be mass or volume. And the molarity, just like molar mass, is the conversion factor, right? That kind of is what I'm trying to link back up here when we were talking about it, that if we're converting between mass and moles, molar mass was the conversion factor we'd put in the parentheses. For solutions, if we're going between volume and moles, molarity is the conversion factor that's going to go in the parentheses. So when you're given molarity, you want to just keep in mind that this is going to be a conversion factor. And we're going to sort of figure out where it's going to go, right? So we're going to start instead with the 2 liter volume. So we have 2 liters of this KOH solution. And in my first conversion step, the molarity tells me that there are 6.00 moles of KOH per liter, right? So molarity is moles per liter, technically of the solution, but you probably don't want to have to write that out every time. So we just canceled out liters of solution. So that makes sense to me, right? That if I know if I have 1 liter of solution, there are 6 moles of KOH. Well, if I have 2 liters of solution, that makes sense. I have 12 moles of KOH, right? I need twice as much because I have 2 liters instead of 1. So then the last thing I got to do here is convert moles of KOH to grams of KOH. And of course, that's just our molar mass from the periodic table. So 39.1 for potassium, 1.01 for hydrogen, and 16 for oxygen. We get 56.11, and that would be the molar mass of the potassium hydroxide. So if I basically just take that number and multiply it by 12, that'll give me my answer. So calculator gives me 673.32, but we need to talk about significant figures. So with significant figures, normally up until now, we've gone back to the beginning, to the measurement, and we've looked at sig figs. We said molar mass doesn't limit sig figs, Avogadro's number doesn't limit sig figs. It just goes back to the measurement. And we can see that the 2.00 liters, right, has 3 significant figures. Now, the problem is that molarity, even though we use it as a conversion, when this solution was made, or as we're trying to make it, the concentration that's reported reveals a certain amount of precision. There are solutions where they need to be pretty exact, and you might need to have it have 5 sig figs, right? Because it's just going to be a very precise analytical titration or whatever it is we're doing. And then sometimes, I can just sort of ballpark it because it doesn't have to be that perfect. So we actually, with molarity, we want to look at the significant figures as well as the volume. So we want to look at both. And of course, least would predict how many sig figs. Since both of these are 3, the final answer is going to be 3. So what we're going to do is round this to 673 grams of KOH. So I would take 673 grams of KOH, and when I dissolve that into 2.00 liters of water, I'll get my concentration at 6.00 molar. So that would be my calculation to help me know, okay, in my 2 liters of water, how much KOH will I dissolve? Okay, so big thing that we've looked at so far is just comparing the last 2 examples. If you're trying to solve for molarity, then make sure you think about using the formula. Moles of solute on top, liters of solution on the bottom. If molarity is given, right, if it's given to you in the question, instead use it as a conversion factor, all right? Now, another formula we're going to have in this chapter is dilution. And it could be used for evaporation, but we hardly ever do that. Dilution is if you take a solution and you add water to it, right? It's going to dilute it. And what you're saying is with this formula that the original molarity times the volume of that original solution would be equal to the final molarity after that total volume now that you've added the water to it. So what the formula says is molarity is moles per liter, volume in liters. So basically we're saying that the moles and the moles stay constant. And if you think about that, that is the moles of the solute. And that's true, that if I add water, which is just a solvent, that doesn't change how much KOH is in there, right? So if I took this 6 molar KOH solution and I add more and more and more water, that only changes the concentration, but the mass of KOH inside wouldn't change, right? The moles of KOH wouldn't have changed. We're just adding water, which is going to dilute it. So as the volume goes up, because I added water, the concentration goes down, right? So moles of solute are unchanged. Only the volume changes, which changes the concentration or molarity. And heads up, a lot of times when you hear someone say concentration, technically concentration can have a lot of meanings. You can have a volume percent, you can have a mass percent, you can have a molarity, but we chemists, we love molarity, obviously, because it has moles in it. So a lot of times if you hear concentration, just assume that that means molarity, unless something else is specified, but we're going to just assume molarity. All right, so here's a question. How many milliliters of a 10.15 molar sodium hydroxide stock solution, which just means this would be the concentrated solution you'd order from Fisher Scientific, would be needed to make 15 liters of a 0.315 molar sodium hydroxide? So if I ordered sodium hydroxide for a lab, when I order it from the chemical company, I'm not going to pay for water, right? So I'm going to buy the most concentrated solution I can buy, and then I'll dilute it to whatever molarity I need it to be. Now, what you want to look for is, because there's a lot of stoichiometry questions that are going to seem very similar, and the M1V1 formula won't work. What you want to make sure and look at is this a reaction? And the answer is no, right? I'm just taking sodium hydroxide and making a new sodium hydroxide. Once you realize that there's only one substance here, that makes this a dilution problem. And if it's dilution, that's when we get to use the nice formula of M1V1 equals M2V2. So the other thing is look for your pairs, and it will usually have of, right? So there's 15 liters of 0.315 molar. That's a pair. And we want to know how many milliliters of 10.15 molar. So just make sure you pick your sets appropriately, and then you just plug everything in. It doesn't matter if M1 is 10.15 and V1 is your unknown, or you could say M2 is 10.15 and V2 is your unknown. Doesn't matter as long as your pairs are correct. So if I just start with M1 and then V1 being my unknown, so 10.15 molar, my initial molarity. Initial volume is what I don't know. I want to know how much of that will I use. My target molarity is 0.315 molar, and I need 15 liters of that. So to solve for V1, I'm just going to divide both sides by 10.15 molar. All right, we got rid of that initial molarity on the left side. So I'm going to take 0.315 times 15.0 and then divide that by 10.15. Keep least sig figs. So I get 0.466 after rounding up because I'm cutting off a 5. Now my volume unit, molarity has canceled out. So the volume unit would be the same as the V2 unit. So it would be liters. So I would need about half a liter of that stock solution. And then I would add about 14.5 liters of water to get the final volume, or sorry, the final molarity at 0.315. Okay, so that would be what we're looking at for that particular question. All right, so this would be the amount of the 10.15 molar solution. And then to that, we would add, let me just take a difference, 15 minus 0.466. And so you'd get 14.5, keeping the decimal place, liters of water to get 0.315 molar. All right. And that would give you the 15-liter total volume. All right. Now, that wasn't what we were looking for. I took that just an extra step. We were just looking for the volume needed. So that what I put in the box, that's the answer. But just so you understand what exactly we're calculating. So if you took that basically half a liter of that concentrated stock solution and then added 14.5 liters of water to get the total volume now to 15, now that concentration would be 0.315. Question was, do we have to convert that to liters? And the answer is no. Whatever volume you're given for V2, just have it be the same as V1. I guess technically this one did specify milliliters. So if we want to make sure it's in milliliters, it would just be 466. But if it doesn't specify, just keep whatever unit it's looking for, or whatever, sorry, I just hit my desk. Just keep the same unit as the other volume unit. But I guess this one technically did ask for milliliters, so we'll go ahead and multiply it by 1,000. All right, then aqueous solutions. So that's all we've been talking about so far anyway. Aqueous solution just means water, again, is the solvent. We're going to start looking at ionic compounds dissolving in water and looking at double displacement reactions. So earlier when we were talking about the sodium chloride, marking it as aqueous dissolves in water, and an ionic compound does that by dissociation, meaning the cation and the anion separate and they go their own way. It's because water is polar, which is something we'll get into much later, but basically it has positive and negative ends like the poles on a magnet. And so it likes other positive and negative particles because that mixes well together. Like dissolves like is always the rule. So if you have an ionic compound in water that dissolves, it has to be soluble. Some of them are not super soluble. The cation and the anion, again, the term is they dissociate. Now, electrolyte to a chemist just means that you have ions. So ion is from a word meaning wanderer, and Faraday was the one who discovered ions, and wanderer because they wander around in solution. And these ions, when they wander, they can carry an electric current. And so that's where that term comes from. A lot of times you hear electrolyte, you think like Gatorade or something like that. But to a chemist, electrolyte just means ions. So something that dissolves in water, as long as it is an ionic compound, it will be a strong electrolyte, but it has to be fully soluble. And we'll start talking about how some compounds are not fully soluble. If you have a weak acid, yes, so dissolving in water, what happens is as long as it is an ionic compound, the ions dissociate, they break apart. So that's all dissociation means, is that those ions are splitting in the compound. They're no longer the compound. Like sodium chloride in water really doesn't exist. It exists as sodium ions and chloride ions. The compound itself, when it dissolves, it breaks up. So that's the dissociation step. If it's a weak acid, so interestingly, all of the halogens, hydrochloric, hydrobromic, hydroiodic acid, those are all very strong acids. Hydrofluoric acid is an exception. And what that means is that it will still dissociate but it doesn't do it to 100%. So it may only go 70% forward or 30%. And I remember this is almost all of Chem 2. Like Chem 2, you spend weeks on equilibrium. Every time we look at equations up in really until Chem 2, we always assume that chemical reaction goes 100% to the right, that everything goes 100% to the product side. But it's not actually true. There's an equilibrium point in the middle. So a weak electrolyte, all I need you to know, because this not 100% dissociation, that really doesn't come in until Chem 2. All I need you to know is that if it is a strong electrolyte, there are lots of ions present, right? So it's very good at conducting an electric current. If it's a weak electrolyte, there are much less ions present. There are some, right? So some electric current. Yeah. Let's see. When you dissolve ions in water, it glows in a dark room. It depends on the ions. But that's interesting. Let's see. Oh, strong acids. Yeah, we'll learn the strong acids later. These are good comments. Okay, so if it is a non-electrolyte, right, this is fun. Non-electrolyte then just means that there are no ions present. Now, there could still be things dissolved in the water, like sugar. Sugar dissolves in water, but it doesn't form ions because it's not an ionic compound. So if you have an electrolytes, what compounds you're going to look for is it's going to be ionic compounds and acids, right? Those are going to be the two that you look for. Because remember when we were doing nomenclature, we talked about how acids were also ionic compounds. They just were special ionic compounds because they always had H as a cation. Okay, so now what we're going to do, we're going to keep all this information in our brain when we get to the next section, is we're going to look at reactions that form precipitates. All right, and these reactions are called double displacement reactions. We saw these in intro, so we're going to look at these again. And the precipitate is an insoluble solid, but technically what I want you to think of, instead of solid, we're going to say an insoluble ionic compound. All right. And if you're thinking, well, wait a minute, just a minute ago, you said ionic compounds dissolve really well in water. For the most part, that's true, but there are some that don't. Now, I would never expect you to remember which ones do and which ones don't. You're going to need what are called the solubility rules to figure that out. So I'm going to be using this. This is posted in the Chapter 5 folder. There's a file posted. It says solubility rules and activity series of metals. But the solubility rules, this would be given to you on the test, just like the activity series of metals. They are listed in order, and in order of dominance. So like rule 1 trumps anything after that, right? And then rule 2 would trump anything after that. So rule number 1, which is an easy one to remember, but you don't have to, is that group 1 metals like sodium, potassium, lithium, those alkali metals, in every compound they're in, they are always soluble, which means they always are going to dissolve in water. So if it is soluble, we're going to mark it AQ, saying it is dissolved in water. Salts containing nitrate, that polyatomic ion NO3 -1, again, always soluble. So iron 3 nitrate or chromium 2 nitrate or magnesium nitrate or potassium nitrate, always soluble. Same is true for acetate, that C2H3O2 -1 polyatomic ion, and chlorate, ClO3 -1. All of these are always soluble no matter what they're paired with. When we get to the halogens, chloride, bromide, iodide, most of the time they are soluble as well, but exceptions here are when they're with silver, lead 2, or mercurous. And we're not going to deal with the mercurous complex cations, so don't even worry about that one at all. But what this is telling me is that if I had PbCl2, right, if I've got lead with chloride, it's going to be insoluble, which means I would mark it S for solid. However, if it's any other metal besides lead or silver, let's say it's barium. If it's barium chloride, barium bromide, barium iodide, always soluble. So soluble, mark it AQ, dissolved in water. Insoluble means it's going to be a solid. Now it says most silver salts are insoluble, meaning they do form solids. However, remember they're in order of dominance. So silver nitrate, nope, rule 2 beats rule 6. So silver nitrate would be soluble. Silver acetate, soluble. Silver chlorate, soluble. But then when I start getting to like silver sulfide or silver bromide or silver, right, then all of a sudden they become insoluble, right? Insoluble, but after not with any of these three. Most sulfates, SO4, again, soluble, aqueous, but again, some exceptions. The group 2 alkaline earth metals a lot of times led to, again, silver and strontium, or another alkaline earth metal. Hydroxide, slightly soluble. What does that mean? That means put S, right? So that's what I put here. That means we're going to mark it S for solid. So I'm going to be coming back to this rather than going through the whole thing right now. We're going to use it as we go through our double displacement reactions. But what happens with double displacement is you have AB, where AB is some kind of ionic compound, and it would be dissolved in water. And you're reacting it with CD, which is another ionic compound dissolved in water. So basically you're mixing two solutions together. What products would you predict? Well, you only have 4 ions here. You have a cation and an anion, A and B. You've got a cation and an anion, C and D. So you're not going to put positive A with positive C. That doesn't make sense. 2 positives don't go together. So one option would be that you put A with D. The other option would be to put positive C with negative B. And then what we need to do is we need to figure out if those 2 compounds are aqueous or soluble. And in order to do that, we're going to need our solubility rules because we're not going to memorize those. All right, I had to memorize them. It's not terrible, but I also think it's not necessary. So you're just going to look back on your solubility rules. So this is what you always look for double displacement. Ionic compound, metal in front, in solution. Ionic compound, metal in front, in solution. So that is always double displacement. So you're like, okay, what I need to do is, and I think this is the majority of getting it right, is step 1, identify what your ions are. All right, understanding those ions is huge. So if you were wondering in nomenclature why I asked you what the cation was and what the anion was, this is why, because I knew where we were headed. So your cation here, sodium, group 1 alkali metal, +1 charge. Nitrate, polyatomic, NO3, -1 charge. Magnesium, group 2 alkaline earth metal, +2 charge. Sulfate, SO4, -2 charge. Okay, so what I'm looking for is what will happen when sodium and sulfate come together and what will happen with magnesium and nitrate come together. All right, so when you identify your ions, this is going to be huge and I'll repeat it quite a bit. Your ion only has a subscript if it's a polyatomic ion, right? We're going to circle back to that when we get to the next example. So we've got sodium, nitrate, magnesium, sulfate. So on the product side, I would put sodium +1 charge with sulfate -2 charge. Now those charges obviously don't balance each other. So just like we did in nomenclature, I would have to have 2 sodiums here to balance the sulfate. All right, and don't worry that you don't have 2 sodiums on the reactant side. You can take care of that later. When you make the product, you have to make sure the charges are balanced. Sulfate we know is -2. Sodium we know is +1. So we need 2 of those to make this compound come together. All right, then the next one here, we've got magnesium, which is a +2, and nitrate, which is a -1. So again, got to balance the charges. We're going to need 2 nitrates to balance the Mg. Now I'm going to check to see, right, aqueous or solid. I go to my solubility rules. Remember, rule number 1 was anytime you've got sodium, it's always going to be soluble. Group 1 metals, no matter what, always aqueous. So you really don't even have to check the rules. Sodium's always soluble. Rule number 2 is nitrate, also always soluble. So that means magnesium nitrate is also soluble. So what does that mean? right? That means that no precipitate formed. And so, from a standpoint of, was this a chemical change? The answer is no. This was no reaction. No precipitate formed. No new matter was formed. All we have are ions dissolved in solution, ions dissolved in solution, ions dissolved in solution, ions dissolved in solution. So the only thing we did here was we mixed things together. And yeah, the solubility rules will be given on the test. You don't have to memorize those. All right, so for that particular question, part A, nothing happened. No reaction occurred for that. All right, now let's look at the second one. Now this is where the subscript thing is going to be important. All right, so going back up here, I should do this. All right, check your ions first. Bank your products. All right, make sure you balance your charges like we did in nomenclature, right? Make sure everything's balanced out. And then check your rules, check the solubility rules to see if there was a precipitate. All right, next one, we've got iron 3 chloride solution and sodium sulfide solution. So when I look at my cation here, cation is iron. It's a type 2 transition metal. Don't necessarily know the charge based on the position on the table, unlike sodium, right, which we know is always a positive 1. Then what I look at here is I got Cl3. All right, and then I want to just think about, yes, we will have to balance the equations. We're going to do that on this next one. What I think about is that 3 subscript on the chloride. Is that part of a polyatomic ion, or is that just balancing charges? And we can see it's not polyatomic because this is a binary compound. The nitrate in the last example, that 3 was part of nitrate. That's a polyatomic ion. So that group, nitrate, stays nitrate. So you'll notice on the product side, that subscript is locked in place. Nitrate has to be NO3. But with FeCl3, that 3 subscript is a charge balance 3. It's only there because in the compound, iron and chlorine have to balance each other. So if I think about chlorine, chloride, right, being -1, there's 3 of them in the compound, so the iron must be a positive 3 charge. So when I write my ions, I don't want any subscripts unless it's part of the polyatomic, right? So nitrate is a unit. I have to write the whole unit. Sulfate is a unit. I have to write the whole unit. But chloride isn't a unit. It's just a nonmetal. So that 3 subscript on the chloride is only there because it's balancing the charge. That's it. The same thing is happening in sodium sulfide. Sodium is a group 1 alkali metal. It's not a polyatomic ion, right? There's 2 of them there only because sulfur is a -2 charge. So when you write your ions by themselves, they should have no subscripts unless they are polyatomic ion units, all right? So when I come over to the product side, I would put iron, which is still a positive 3. The charges don't change, and double displacement. And I'm going to partner it with sulfur, which is a -2. So just like we did in nomenclature, we're going to crisscross here, or least common multiple would be a 6. We need it to be Fe2S3. The other compound we've got here is sodium +1, chloride -1. Those charges are balanced, so we just leave that alone. Most common mistake I would get on this is that a student would just put FeS and then they would put Na2Cl3 because it's just taking Fe with S and Na2 with Cl3. Hopefully, though, when you look at that, you're like, well, that can't be right because sodium's +1, chloride's -1. Why would those subscripts be there? And you're right, they shouldn't be. Remember, with nomenclature, the charges have to balance with an ionic compound, and we always want the simplest way to make that happen. And in the iron 3 sulfide, right, FeS wouldn't work because those charges don't cancel out. So that's where double displacement gets just slightly more complicated, is that the subscripts don't necessarily carry over unless they're polyatomic ion subscripts. In that case, they are locked in place. You cannot leave them. But if it's just a charge balance subscript, On the reactant side, it's there in the compound, but on the product side, it's a different compound, different charge balance, so you may not need them. Now I'm going to go to my solubility rules. Remember, we said sodium always aqueous no matter what, so we don't really have to check the sodium chloride. We know it's going to be soluble. So the next one we've got is the iron 3 sulfide. And there is rule number 9, which says most sulfides, right, S -2, of transition metals, which would be iron, copper, zinc, right, are insoluble. And iron 2 sulfide is listed. Iron 3 sulfide would also have the same role. So sulfides with transition metals are insoluble. Insoluble means that's going to be our solid precipitate. So in this one, if we were in lab and we added a squirt of iron 3 chloride solution and a squirt of sodium sulfide, we would see that thick precipitate form. Now we are going to balance. That was the next question. Do we have to balance? And the answer is yes. Now, when you balance, right, this would be step 4, right? So step 4, always the last step is the balancing step. And when we balance with coefficients in front. All right, so when I go through the motions of double displacement, step 1, identify your ions. Step 2, make your products based on those ion charges, canceling out the charges using subscripts as needed. Next, step 3, we check the solubility rules to figure out which one was the solid, if either of them were, right? First example, no, but this example, yes. And now the last step is balancing, and this should be the easy step. If it's not, it's probably because one of the products wasn't right. When we balance the equation, we use the coefficients in front. So different numbers, right, have different purposes. Sometimes a subscript is there because it's part of the polyatomic ion unit. That subscript is locked in place. Sometimes a subscript is there because it's just balancing charges. That's only important in the compound. When I break up the compound and look at the ions, that subscript goes away because I don't need it. Charges separately don't have to balance. Only in the compound do they have to balance. Then we come to the product side, we use new subscripts to get the charge balance for that particular compound. So subscripts are there to balance charges or because they're part of the unit. When I balance both sides of the arrow, reactants and products, I use the coefficient in front. There's not a great place, like a perfect place to always start, but after my many years of doing this, something I've always picked up on is that if you have a product where you needed charge balance subscripts to make it all come together, that's usually where I start. So for example, I needed 2 irons to make that iron 3 sulfide come together. When I check the reactant side, I only have 1 iron. So I'm going to put a 2 in front of FeCl3. So I have 2 irons on both sides. Now I also am going to check the sulfur, right? Because I needed a subscript of 3 on the product side to make that iron 3 sulfide work. On the reactant side, I've only got 1 sulfur. So I'm going to multiply sodium sulfide by 3. Then hopefully that means I'm going to keep a 1 in front of the iron 3 sulfide. And the only thing I'm going to need at the end is how much sodium chloride to balance. So 2 times 3, I have 6 chlorines on the reactant side. 3 times 2, I have 6 sodiums on the reactant side. So I've got 6 of both. So I'm going to put a 6 in front of sodium chloride. And now I've got a balanced double displacement reaction. All right. So this is called the molecular equation because everything is in a compound or molecule format. We're going to look at ionic equations in just a second, but we're going to do one more of these. So next example, we've got barium nitrate. So we've got barium group 2 alkaline earth metal plus 2 charge. Now remember, the nitrate is a unit. It's a polyatomic, but the subscript of 2 on the nitrate is only there to balance the charge on the barium. So when I write my anion here, it's just nitrate -1. Now, again, these charges don't balance, but that's okay because now that the ions are separate, we don't care if they balance. It's only in the compound when they're together that we have to make sure that they're balanced. Sodium sulfate, sodium group 1 alkali metal plus 1 charge. Sulfate, again, another polyatomic unit. So that 4 is part of sulfate. It is locked in place. We can't leave it alone. We can't leave it. We got to have it as SO4 -2. So then when I come to the product side, I need to put barium, which is a +2 charge, with sulfate, which is a -2 charge. So those charges cancel out. That looks good. And then I'm going to put sodium +1 with nitrate -1, and those charges also are balanced and look good. All right, now, next step is I go and figure out if I had a solid. Again, sodium, always soluble, don't even have to look. So let's look at barium sulfate. So the rule here was most sulfate salts are soluble. Exception would be barium sulfate. So barium would be insoluble. So barium sulfate, insoluble, that means the solid. So we know that's going to be the precipitate. All right, so insoluble, just for your notes, means it's going to be the precipitate. Now, last step is balancing with a coefficient in front. 1 barium, 1 barium, 1 sulfate, 1 sulfate, 2 sodiums on the reactant side, 2 nitrates on the reactant side. So sodium nitrate on the product side needs a 2 in front. And now I've got a balanced equation. So balanced molecular equation. All right, let's look at another one. I've got zinc sulfate and calcium chloride. So cation, zinc, +2 charge. Sulfate, we just saw this one, SO4 -2. Calcium, group 2 alkaline earth metal, +2. And then that chloride, again, not a polyatomic. So we just want to look at chloride by itself, -1. Now, a little bit of a heads up. If you're doing a problem and you're like, this seems too easy, here's something that can make you feel a little bit better. I mean, that's always a good thing if it seems too easy. But what I mean by that is if you have cations that have the exact same charge, that means that they are literally just going to swap places, right? If you had it where the anions had the exact same charge, again, it would be where you just swap places. Oh, in my notes, this is barium instead of calcium. Okay, it would work the same. I think because we just saw barium up here, I changed it to calcium, and I may not have changed that on the notes, sorry. So if this was BaCl2, it would look exactly the same. But I wanted, because we had barium in the last example, I figured I'd change it just a little bit. All right, so we've got zinc partnering with chloride. And again, to get that charge balance, it should be ZnCl2. And then we'd have the calcium, +2, with sulfate, -2. All right, and those charges are balanced. Then if I go to my solubility rules, okay, chloride, it says here, chloride typically soluble except for silver or lead. Well, I don't have silver or lead. I have zinc, and so that means it should be soluble. The calcium sulfate, that was the same rule as the barium sulfate. Sulfates are typically soluble. Calcium, though, is an exception. The alkaline earth metals, we actually do a lab on this right after the midterm. We're going to see where those are insoluble precipitates. Barium, calcium, strontium, magnesium a little bit, but not quite as much. Okay, so I've got a balanced equation at this point. Remember, this one was easy because the cations had the exact same charge. When that happens, they literally just swap places, and then it's good to go. So that's our balanced molecular equation. Now, what we're going to also practice here is called the complete and net ionic equation. So I have to say, as a student, I did not like this. I mean, it's not bad. It's just, here's the idea behind it. We've got a chemical reaction. Now let's express it 3 different ways. That seems a bit, I don't know, redundant. But you could argue whatever you want. So this is just one of those 3 ways. This is balanced, right? We didn't need any coefficients up front. We got the same number of zincs and chlorides, everything on both sides. So it's balanced. Molecular, meaning again, everything is in a molecule or compound format. So this is our balanced molecular equation. So this is, I'm just going to rewrite it. This is one way of writing this chemical reaction. So balanced molecular is the ZnSO4 aqueous reacting with the CaCl2 aqueous to make the ZnCl2 aqueous and CaSO4 solid. All right, so balanced molecular equation, one way of expressing this reaction. The second way, this is my least favorite way. This is the total ionic, also sometimes referred to as the full ionic equation. We're going to take all that information in the balanced molecular equation. We're going to rewrite it, but we're going to make it slightly more complicated. Now, granted, the total ionic equation is really more accurate, but it doesn't really tell us anything new. So I think as a student, that's where I was like, this is telling me the same thing. So why am I writing so much more? Here's what happens. Remember when we were talking about if it's an ionic compound dissolved in water, it dissolves by dissociation. It breaks the compound up into ions. So the ionic equation, that's your cue, which is show me the ions, right? Because really that's more accurate. The zinc sulfate in water really doesn't exist as zinc sulfate anymore. What happens is it exists as zinc cations and sulfate anions, right? So we're going to take zinc sulfate and we're going to just rewrite it as zinc plus sulfate, right? And we're going to break it up. But here's what's important, and this is huge. All ions need charges. All right, this is the big deal, all right, because there is a big difference between zinc with no charge and zinc +2 with a charge. If I just wrote this as zinc by itself and sulfate, right? What this is, zinc with no charge by itself, that's zinc metal. And that's not what we have here. SO4 is a compound that doesn't exist. So SO4 -2, that exists. That's an ion. It's got 2 extra electrons, so it's happy. The zinc, no charge, that would be zinc metal. And that's not what we had. We had zinc ion dissolved in water. So the charges are super important. And you may not think it's going to be that important, but it's a huge point deduction with the ionic equation if you don't have the charges. So just know if it's an ionic equation, you better have all your charges there because really, again, we want to be accurate. So it's got to be the zinc ion in water, not zinc solid in water, right? With the sulfate, right? The good news is though, is you've already identified the ions. They don't change. You just have to rewrite them. So the second compound, let me look at that. You had your calcium. Oops, I should have done it down here. You got your calcium chloride. So what I'm going to have is I'm going to have my calcium +2 alkaline earth metal, and I'm going to have my chloride -1 halogen. All right, now notice there's something special going on here. That 2 on the chloride, that's subscript of 2. Remember how we said it wasn't a polyatomic ion 2, it was a charge balance 2. Which means it's not locked in place like the 4 was for the sulfate, because sulfate's a group. It has to stay SO4. What happens here is that 2 moves to the front of the chloride. So when you have a calcium ion come together with chloride ion, you have to have 2 chlorides, right, to make the charge balance. In the compound, it has to be written as a subscript. When we separate them, we move that subscript to the front, all right? So I'm going to write a little note here. Charge, balance, subscript moves to the front of the ion, all right? And I'm just going to give that the little red star so you can figure out that's what I'm referring to. All right, so the zinc sulfate, we broke up into zinc and sulfate ions. The calcium chloride, we broke up into calcium and chloride ions. Then when we get to the product side, we've got zinc chloride, still aqueous, so that means we should still break it up. So the zinc ion And those two chloride ions are still separate, right? So I'm just going to kind of show this. This is this that we just wrote this way. All right. And again, that subscript of 2 on the chloride became the coefficient of 2 in front, right? Because we broke up the ionic compound. And then my last substance here in the equation is the calcium sulfate. Now that was the solid. So that calcium and sulfate, when that comes together, that sticks together. So the solid stays together. So the solid you don't break up. All right. Only the aqueous compounds do we break up. All right. So your calcium sulfate stays the same. We don't change the solid. Solid stays together. All right. So little note here. Solid stays together. Because that was the chemical change. That's the formation of the precipitate. Like if we did this reaction in lab and I asked you, hey, was this a chemical change or a physical change? You would have said, oh, I saw a precipitate form. So definitely new matter. You wouldn't necessarily know, maybe you didn't know what it was, but you would say, well, I saw the matter form, like I saw the precipitate. So definitely a chemical change. So that is the change here. It's the ions that start out separate, floating around in solution. And then when we mix them, they come together and they stick together. So total ionic, again, my least favorite of the 3 types of equations because total, everything is there. Yeah, I understand, Malcolm. You'll see though, I tried to make it where this may not be quite so bad typing it in. You'll see. I tried to spare you because this was my least favorite of the 3. So everything is there, right? That's why it's the total or full ionic. Everything is there. All your ions have charges. Right. Honestly, it's a lot of writing and it really doesn't tell us anything we didn't already know. My favorite of the 3 is called the net ionic equation. And net, right? Just like gross versus net. Net is the money is what was the change? What happened? Get rid of the stuff that doesn't matter. Just show me what the change was. And if a lot of students, they'll do the balanced molecular, they'll do the total ionic, and then they'll try to get the net ionic. And that's totally fine. If you're more comfortable going step by step by step, absolutely do it. Net ionic, really what you're doing here is you just want to show what makes the solid or the precipitate. So if it were me, I would prefer not to have to write the total ionic equation. If I can kind of think ahead and say, okay, well, the calcium sulfate is what made the solid here. So I know that I need to show in the net ionic equation what made that, right? That's my job with net ionic. That's the chemical change. So what do I need to make that? Well, I know that the cation here would have to be the calcium plus 2 alkaline earth metal. And then the anion here would be the sulfate -2 polyatomic, right? Now, what you could do is if you write out the total ionic equation first, you can cancel out what are called the spectator ions. Spectator, I love that term, whoever came up with it, right? Like these ions are just watching what happens. I mean, okay, we'll go with that. So the idea is that when I started this reaction, I had an ion of zinc. When I finished this reaction, I had an ion of zinc. So really the zinc wasn't used. So that it's a net of 0, right? I didn't use any zinc. I came in with the reaction with zinc. I left with zinc, right? The ion wasn't used. The sulfate turned into a solid. The calcium turned into a solid. That's important. The 2 chlorides, again, didn't use those either. So you can almost think of your arrow like an equal sign in math. And if you have like terms on both sides, you just subtract them, right? They cancel out. So the zinc ion cancels out, the 2 chloride ions cancel out. And what you're left with is the calcium and the sulfate ions coming together to make the calcium sulfate. So if you're more comfortable writing out the total ionic, canceling everything out, and then getting your net, absolutely do it that way. If you can, I always like shortcuts if I can do it. So what I noticed from my balanced molecular is the calcium sulfate made the solid. So that's what I want to show. Notice in all 3 equation types, the calcium sulfate does not change. That is the new matter formed, right? So we got to show that. So then Ionic, we're still focusing on the ions, right? So what is the cation that I need? What is the anion that I need? Add those together to make your product, right? So net ionic, I like those. I like those. I like the balanced molecular okay. I just didn't like total ionic. All right. So when writing net ionic equations, do we need to write the cation first or the anion? And it doesn't matter. Good question. So question was, if we had done it this way, where we had canceled it out, we may have been tempted to write sulfate first, just rewriting it, and the calcium second, and then making CaSO4 solid, right? Either way is totally fine. As long as your two reactants are the same, maybe you just switch the order, totally fine. The same is true, let me scroll back up here. The same is true with the molecular compound. Like if you wrote calcium sulfate first and zinc chloride second, totally fine, right? The order of the products doesn't matter as long as your two products and my two products are the same. And same with any of the ions. The order doesn't matter as long as you have the same four that I have. All right, so that's actually a perfect place for me to stop. So we're going to stop here. We're going to come back at 12:30 into the part 2 Zoom room, but I'm going to go ahead and get this recording starting to convert over to an MP4. So I'll see you in the second space at 12:30. Have a nice little break. I'll see you just in a little bit.